Okay, in today's video we need to talk about how some ions on the periodic table have charges that can be easily predicted and some do not. So we need to talk about the ones that can be predicted. Okay, so last video, we were talking about the periodic table. This is a clean one. I know I wrote all over the other one. I'm probably going to write on this one too. And we said that basically these things are organized by size, or by number of protons, by atomic number, but that things in the same column tend to have similar properties. We're going to use that feature to predict some trends here. So the idea is, if given the opportunity, and not every element can do this, if given the opportunity, most elements, most atoms, I'm going to kind of anthropomorphize them here. Sorry, I can make them sound like people. They want the same number of electrons as the noble gases, which is column 8A on the periodic table. So that's these guys over on the far right. So this is helium, neon, argon, krypton, xenon, radon. They're the most stable elements on the periodic table. They don't form charges. They're just happy to be where they are. I'm fully aware they're not happy, they're stable, but whatever. Okay, so the idea is, if you have an element like, let's say, sodium. Sodium is element 11, okay? We do the proton, electron, neutron thing. We're not gonna have to think through this every time. I'm just doing it as an example. This should have 11 protons. If it doesn't have a charge, which it doesn't yet, it will also have 11 electrons. And I don't know, let's say it's 23, not that it matters a whole lot, but this would be 12 neutrons. The neutrons is not gonna affect any of this. Okay. So if we look at element 11, the nearest noble gas is actually element 10. So it's in between neon and argon. So sodium can either lose 1 electron and become positive to be like neon, or it can steal 7 electrons to be like argon. Atoms typically take the path of least resistance, so it's going to do whichever of those is easier. So this will lose 1 electron to be like neon, which is super stable. Okay, so the result is it forms a +1 charge. It's not exactly the same as neon, but sodium with a plus charge is similar to neon. It's as close as it can get. Okay, it's not perfect, but the idea is neon has a atomic number of 10, which means 10 electrons if it's neutral. Sodium plus also has 10 electrons because it will be losing 1 to form this +1 charge. So as far as number of electrons, this is as close to being like a noble gas as possible. Okay. So similarly, if we looked at another example like sulfur. Okay. Sulfur has 16 electrons. I'm just going to skip to the point here. I'm assuming if you watched the last video, you know how to figure out protons, electrons, and neutrons. 16 electrons normally if it's neutral. The same noble gases are the same option. It's in between neon and argon. It could lose 6 electrons to be like neon, or it could steal 2 from somewhere to be like argon. Stealing 2 is this path of least resistance, so that's what it's going to do. Okay, so if it gets a 2- charge, basically if it gains 2 electrons, what will happen is that this will basically give it 18 electrons total. This will make it equivalent, I guess, not exactly the same. As far as electrons are concerned, it'll make it equivalent to argon, which has 18 electrons. So it's as close to being a noble gas as possible. So the idea is things that can, usually they won't gain or lose more than like 3 electrons. Anything that is typically within like 1, 2, or 3 electrons away from being like a noble gas will tend to gain or lose electrons until they are like a noble gas. So this means we can predict some trends. we saw that sodium forms a +1 charge because it can lose 1 to be like neon. Well, it turns out that lithium is 1 away from being like helium, potassium is 1 away from being like argon, rubidium. So everything in this column tends to form a +1 charge. Okay, everything in column 1A. So it turns out that anything in column 1A, if it's going to form a charge, is always +1. It can be 0, it doesn't have to have a charge, but if it's going to form a charge, that's the charge it's going to form. By that same logic, anything that's in column 2, this is 2 away from being like neon. This is 2 away from being like argon. Anything in column 2A is always +2 if it's going to form a charge. Okay. This little dip, this valley in the middle here, this little no man's land, is kind of going to be a problem. We're going to have to deal with that later. But for right now, aluminum is the only other metal that we know how to predict. Aluminum always forms a +3 charge. So, as far as metals, those are the only ones that we can glance at the periodic table and consistently know what their charges are. The problem is all of the rest of them can actually form more than one possible charge, and we're going to have to deal with that later. But for right now, we're just looking at the ones that we can easily predict. Looking at this from the other direction, so these ones were 1 away from being like a noble gas by losing an electron. These are 1 away from being like a noble gas by gaining an electron. So anything in column 7A, which are the halogens. It's one of the few names that pops up a lot. The halogens basically always form a -1 charge. Okay, so we can just glance, we know that if they're in that column, that's what they're going to do. And a similar trend happens here. Column 6A is always -2. Column 5A is -3. Okay. So out of the periodic table, we can predict all of column 1 are going to be +1, all of column 2 are going to be +2. We have no idea what to do with all the rest of this. Aluminum is +3. For the non-metals, these don't even form charges. This is -1, -2, and -3. Anything that's touching the stair step or below it, we don't know how to predict it. Okay. Things like carbon, which is super abundant, tends to find a new route. It doesn't actually form charges, it has a different way of bonding. We'll deal with that much later. Okay, so what do I will need you to memorize this. So I'm gonna write that on here just so you know. Unfortunately, I can't, you have to have some things memorized in order to work in chemistry. This is one of them. These charges that you can predict, I just need you to know them, okay? So if you can understand how they work on the periodic table and why we're getting those numbers, it's easier than just memorizing some numbers. So let's talk about what to do with this. Let's talk about ionic compounds. Ionic compounds always have a cation, which is positive, and an anion, which is negative. We talked about those in a previous video. Okay. The general way it works is we need the charges to cancel out. So they are overall neutral. In other words, we can't have like an overall positive charge on a salt or on an ionic compound and have it work out. Another word for ionic compound is salts. When you talk about like table salt, we're usually talking about sodium chloride or potassium chloride or potassium iodide, some variation of those. Okay, there are billions of types of salts, and honestly, we're going to talk about the broad term salts, not those specific ones that you use on food. So the idea is you just need the charges to cancel out. So like the examples we talked about before, if you had sodium and sulfur and they were going to form a compound, I'm actually going to get rid of that plus sign, might be confusing at this point. The charges that we would predict for these is we said this would be +1 and this is -2. In the real world, you will never just have one atom reacting with one atom. You'll have trillions and trillions of these interacting with trillions and trillions of these. So what we find is that if we need more than one of either of these, they're always there. There's plenty to go around. So in order to make the charges cancel out, we have a sodium and a sulfur. We will actually need two of these to cancel out this. Okay, so you would just write it like this, but essentially if you had two of these, this would be overall +2, and one of these would be overall -2. The charges cancel out, so we end up with a neutral salt. The way we write it is the subscript tells us that we have two of these. Okay, so the red part we wouldn't typically write in there, I'm just trying to point stuff out. So this compound, in order for it to be neutral, is Na2S. Okay, similarly, if you had, pick another couple of examples that we know how to predict. Okay, let's say we had magnesium and bromine. Okay, magnesium is in column 2, so it should be +2. Bromine is a halogen, it's in 7A, so it's going to be -1. So, kind of the same idea, but kind of the opposite. Okay, it's the same idea but reversed. Basically, this is +2, so we're going to need two of these to cancel it out. Okay, so it'd be MgBr2. Okay, one way to visualize this that sometimes helps is if you have Mg with a 2+ and you have two Br minuses in the area. Basically, one of these +2 charges will neutralize that, and the other one will neutralize this, which is why we need two of those, which is what this subscript tells us. Okay, so this is just how to visualize it. Okay, let's try at least one more example, and then we'll stop this video, I guess. Let's do potassium and aluminum. Oh wait, sorry, those are both positive ones. Let's do aluminum and oxygen. Let's do that. Okay, so aluminum, we said, is 3+, and oxygen is 2-. Okay, so basically to make this work, we can't just like double this like we were doing in these previous ones. We're gonna have to put a little more effort into this. What we need to do is find the least common multiple between these two. So it turns out that between 3 and 2, the least common multiple is 6. So if we have 2 aluminums, that would add up to +6, and 3 oxygens would add up to -6, which means they would cancel out. And this stuff can't be like scaled down to a reduced number, so that's gonna have to be the final answer we live with. So this is the formula. So basically, 2 of these would be +6, and 3 of these would be -6. Okay, all right, we'll stop there. We'll continue this in another video. Thank you.